Hey AP Chemsters, this is Mrs. Vanderwaaly, and we are going to continue our discussion in Chapter 11, which is all about solutions. So Section 11.5 is the boiling point elevation, the freezing point depression, and in effect, this is the introduction to colligative properties. A colligative property is dependent on the number of solute particles, but not necessarily the identity. So in other words, sodium chloride will have the same effect on the properties as ammonium nitrate would. It doesn't make a difference if it's sodium chloride or if it's ammonium nitrate. The three colligative properties that we'll be talking about is the boiling point elevation, the freezing point depression, and the osmotic pressure. First of all, the boiling point elevation. Let's kind of go back and think about what is the boiling point. We defined that back in chapter 10 as a boiling point is the temperature at which the vapor pressure of the solvent or the solution here is equal to that of the atmospheric pressure. So if the atmospheric pressure is at 1 atmosphere, then where water boils is where its vapor pressure is also equal to 1 atmosphere. There's enough gas molecules being created to have that much pressure. That's actually defined as the normal boiling point. If the atmospheric pressure is actually less than that, like at higher altitudes, then it takes less gas molecules to have that equal pressure, so that's why the water will boil at a lower temperature, let's say in Denver, than here in Cincinnati. So how does a solute being added to the water affect boiling point? Well, let's think about it. A solute is either an ionic substance or a polar substance, and either way there is definitely an attraction between the water molecules and either the ions or the other polar solutes. And this attraction is going to bind those water molecules to the solute, and it's going to take more energy to release those water molecules, to separate those water molecules from the solute. So because of this greater energy, it's going to have a higher temperature to actually make the right number of gas molecules than before. So there's actually a video that I made today that will show you that the boiling point of a salt solution is higher than that of a pure water solution. Chemisters, this is Mrs. Vanderwaaly. We are watching water boil. And over on the left, this is the beaker that has the salt water in it, and it's boiling. And if you look at the thermometer, it says 103.3 degrees. Over on the right shows the water without any solute in it boiling, and it is at 99.9. So hopefully this shows you that water with a solute such as salt boils at a higher temperature than without. Okay, so you should have written something down here under the demo. And again, the reason that water with a solute boils at a higher temperature is that the water molecules are attracted to the solute and takes more energy to separate them and become that gas phase, and the temperature will go up. So the question is, okay, why does the freezing point lower? Well, it's the same exact idea that if these solute molecules are attracted to the water molecules, then it's going to be has to take a colder temperature or less energy for them to become a solid. So it's written here that molecules cluster in order to freeze. They must be attracted to one another to have a spot in which to cluster. We saw back in section 11.3 that solute molecules will get in the way. They're actually in between these water molecules. So the more ions in solution, the greater the effect on the freezing point and the boiling point. A solution does not have to have a sharply defined freezing point, but a solvent will, the pure solvent will. And then it says useful for separation purposes and fractional crystallization. You can use this property to separate out different things when they solidify. We won't really be too concerned about that in AP. Okay, problem 15. Why do the road crews put salt on the roads when conditions get bad? Does salting the roads work at all temperatures? Why don't you pause this, jot down your ideas, and I'll be back. Okay, hopefully you wrote down that the road crews will put salt on the roads when conditions get bad to lower the freezing point of water. Therefore, the water will remain a liquid at a lower temperature than 32 degrees Fahrenheit. Does salting the roads work at all temperatures? And the answer is no. I believe the temperature is 18 degrees Fahrenheit, that the calcium chloride solution will no longer affect the freezing point of the water. It will still freeze with the calcium chloride in it. If you remember when we had our polar vortexes and the temperature got really, really cold, that they would end up using beet juice and sand because the calcium chloride would not be affected anymore because it was just way too cold. All right, the third colligative property is osmotic pressure. This is a very important concept in biology, and especially like in the idea of kidneys and in the blood cells. We don't really talk too much about this in AP chemistry, but it is still a colligative property. So what is osmotic pressure? Well, what is osmosis first? It's the flow of the solvent molecules into a solution through a semi-permeable membrane. And that's kind of looking at the picture on the left. What happens if you have this semi-permeable membrane? The solvent, the water typically can go through it, but the solute does not. So the pure solution is free to move on either side, but the solute is stuck on let's say this side, the right side here. So how is this effective? Well, if you look at the picture on the right, you will notice that the pure solvent is actually flowing from the left more to the right to make the solution less concentrated. And when this equilibrium is established, the difference between, in a sense, the two sides pressure there is what they call the osmotic pressure. Again, this is a very important concept when we talked about dialysis and the idea of your blood cells either having too much water in them or not enough in them. Just kind of an FYI here, solutions that have identical osmotic pressures are said to be isotonic solutions. Again, that prefix iso means the same. Fluids administered intravenously, like IVs, must be isotonic with body fluids. For example, if red blood cells are bathed in a hypertonic solution, where a solution having osmotic pressure is higher than that of the fluid cells, then cells will actually shrivel up because the transfer of water will go out of the cells, and that would be bad. So anyway, a very important concept in biology, but let's go on. All right, so then 11.7 is colligative properties of electrolyte solutions. Now, what is an electrolyte? Electrolyte is usually an ionic substance that when it is dissolved, it breaks up into ions. It's called an electrolyte because it will conduct electricity then. So these electrolyte solutions, having these different number of ions will contribute to the different effects of the colligative properties. We call this idea of having the different number of ions called the Van't Hoff factor, and we abbreviate that as an I. So an I is defined as the moles of a particular solute or particles in solution divided by the moles of solute dissolved. So let's keep our math easy. What if we had 1 mole of sodium chloride? Well, how many moles of ions will you have in solution? Well, you'll have 1 sodium and 1 chlorine, and you'll have a total of 2. So the I factor is 2. So if you were to look at these examples below, you will see that NaCl then will have an I equals 2. So you have 1 sodium ion and 1 chloride ion. So what do you think about barium chloride? How many ions will break up when the barium chloride dissolves? Well, I will equal 3. So what about aluminum sulfate? Why don't you go ahead and write down what you think I ought to be here. If you said I equals 5, you're right. You end up with 2 aluminums and 3 sulfates. So the question then is, if calcium chloride having an I factor of 3 is better at lowering the freezing point than, say, sodium chloride, why don't they salt the roads with aluminum sulfate? You're going to have even a lowered a freezing point by putting aluminum sulfate on the roads, and that is correct. Now, think about what other factors go into the road salt. Aluminum sulfate is more expensive than calcium chloride. Aluminum sulfate is not very good for the environment. So there's other factors than just lowering the freezing point goes into why they pick calcium chloride. Now, what about letter D? It says think carefully. What is letter D? C12H22O11. Is that ionic? Is it an electrolyte? And you should say, no, it's not. It's actually sucrose. It's your table sugar. It's what you put in your Frosted Flakes. So when you put sugar in solution, does it break up into different particles? No. So your I factor here is 1. When you put 1 mole of sugar in solution, you get 1 mole of sugar particles. So there is no difference here. So they don't put sugar on the roads when the roads get cold. So let's look at the particulate level. And if you look at the picture on the left, what are the effects then of looking at sodium chloride in a particulate level? You'll see that the chlorides are surrounded by waters, and the sodiums are being surrounded by the water. What we'd like you to do now is draw your own picture if calcium chloride were dissolved in water. So why don't you pause this? I'll put this on the board, and then we can compare answers. All right, so here is my poor artist's attempt at drawing these pictures of calcium chloride, but hopefully you can still see what I was trying to do. Number one, if you look at the ratio of sodium to chloride ions on the left, it's a 1-to-1. There's one purple sodium for every one chloride. Here, it's a 1-to-2 effect. I have 1 calciums for every 2 chlorides in solution. So what is the effect here? Well, I have more water molecules being bound by the ions than in sodium chloride. Also notice that the oxygens are attracted to, I goofed. Take that back. Okay, we'll try this picture again. Once again, we have a 1-to-2 ratio of calcium to chloride, so I have 2 calciums and 4 chlorides in the diagram here. And what I tried to show you before, which my picture was wrong, but now it's corrected, is that the positive calcium ions are attracted to the partial negative ends of the oxygens, and that the negative chlorides are attracting the partially positive ends of the water molecules. A couple other things to notice that I try to show in my picture is that there are fewer freed up water molecules. So more of the water molecules are bound to the ions than before. So it's going to have the effect of that boiling and the freezing point depression like we showed below. So the question now for part D is, what is the effect of putting ionic compounds with larger Van Hoff factors in solution? Why don't you pause this, answer it, and then we'll check our answers when I come back. All right, so hopefully you said that the more ions in solution will have a greater effect. It'll make the boiling point higher, and it'll make the freezing point lower. Like I tried to say before, by putting aluminum sulfate on the roads will indeed make the freezing point lower because of this binding idea that it's interfering with the ability for the water molecules to become a solid, and it will bind the water molecules to take more energy to free them to become a gas. So you are going to increase the range at which water is a liquid, the larger I factors that you have. Now, if you don't believe me, I have a video coming right up that will show you the boiling of sodium chloride versus calcium chloride, and that will then conclude this lesson. Hello, this is Mrs. Vanderley. I am here showing you the difference between the boiling of the sodium chloride and of the calcium chloride. So over here is sodium chloride's boiling point on the left, and it does say 103.3. I hope you can see that. Oh, 103.2 now. But over here on the right is the calcium chloride, and it's at 105.6. So the calcium chloride solution is definitely boiling at a higher temperature at 105.6 to the sodium chloride, which is now at 103.2. So hopefully that shows you that the Van Hoff factor does indeed play a part in the boiling point elevation.